Today I would like to tell you something about how to develop CANopen FD devices, or even if you're not using CANopen at all, maybe you would like to develop simple CAN-FD devices, and you would like to find your typical challenges that you have to solve in order to get to your device. So what's my agenda for this presentation? After a short introduction of myself and the motivation, I would like to talk about the 4 challenges you typically have when you're going the path to develop a CANopen FD device. Challenge number 1 is the specifications. You need to get an overview into the specifications, and some of them you have already seen, they already have presented. Challenge number 2, and this is a very big new challenge, is the physical layer when you jump into the CAN-FD area. Challenge number 3 will be the selection of a CAN-FD controller which suits your needs, your requirements, and the last but not least challenge is the software. On top of that, that's the protocol stack. Let's start with a short introduction of myself. My name is Uwe Koppe. I studied electrical engineering at the University of Armed Forces in Germany, in Munich. I'm head of engineering at the company Microcontrol, and since several years, I'm the elected technical director of the CAN in automation. And as you have noticed, I'm somehow involved in development of these CANopen specifications. So what is now, from the point of view of my company, our motivation in order to use CANopen FD? It's, in other words, it's the need for speed. So to say it nicely, it's data throughput. From the picture you can see here, we have a classical base frame format using 8 bytes, what you know from classical CANopen. And if we use that frame format with 8 bytes at a typical bit rate of 500 kilobit, this frame would have a length on the bus of 222 microseconds. So what happens if we're switching to FD base frame format using 64 bytes, but not using bit rate switching at all? That would mean that this frame has a length of 1.1 milliseconds. You can see the timings in here of what the frame size is in microseconds. So in the table beyond this drawing, you can see the frame size, the frame length, and the net data rate, which is resolving from that. So that means even if you're just using CAN-FD format using this 64 byte, you have nearly doubled the data throughput. And that's a big deal, and this is nice. So, but in the end of the day, your boss will ask you, well, why are you not using bitrate switching? Because that, again, improves the timing. So if you're using the same frame format and using, for example, here, oops, my mouse is very noisy today. If you're using here situation with running 500 kilobit and 2 megabit in a data bit rate, then you will see that the frame length is roughly about 328 microseconds, which leads to the net data rate of 1,560 kilobits per second. So you increased your data throughput very much if you're using CANopen FD, using it with bitrate switching. So that's, in the end of the day, the motivation to use that. So again, from our point of view, what are our milestones to CANopen FD? We started with CAN-FD in 2016 with our first internal CAN-FD based prototype. So a little bit playing around with silicon, which was available at this time. In 2017, we released our first FD-IO modules with CANopen. In 2018, we released our, based on these developments, our CANopen FD protocol stacks. in 2019, we started a development for a customer with CANopen FD based PLC for a customer. 2020, that was the year of Corona. So we started in that time specific FD and CANopen FD webinars based on that technology. And 2021, from our point of view, was really a breakthrough with CANFD and CANopen FD projects. So we did in this year lots of consulting and customer specific development for CANopen FD but also for CANFD for projects will have nothing to do with CANopen at all. But we can see that the market is going to FD. Now, we're jumping into challenge number one. We have to have a look at the specifications. And as you have already seen from Meiner Zitzmann and Oskar Kaplun, they gave you an overview over the specifications. And typically, you directly jump into the CANopen FD specifications. But at this point, I would like to get your eye on specifications which are not related to CANopen at all. They're related to CANFD. And these, I selected here the specifications from the series CIA 601. They're divided in several parts, and the major headline of this specification is CANFD node and system design. And within these specifications, the physical interface implementation is described, the protocol controller interface is described, also system design recommendations are given there. And very important, we see that later, is part 4 for signal improvement, and also part 6 for cabling. Why I'm saying that? Because FD is different to what you might already know from classical CAN. So it's a good starter to have a look on these typical specifications related to CANFD, not dealing with higher layer protocols at all, and get familiar about the specific wordings and the specific extensions which you need to know when you do your hardware and software development. Of course, then the next thing you have to read or to evaluate are CANopen FD specifications. So Rainer already mentioned here the CIA 1301, the CANopen FD application layer and communication profile. This is a must-have. That's your Bible then for CANopen FD. And Oskar also already introduced other specifications on top of them, additional layer applications and things like that, and the new layer setting services. You already might have noticed that when we are talking about device profiles on top of CANopen FD, that these profiles have not changed their numbering scheme at all. So the number keeps the same, like the former CIA 401 for generic IO device is still a 401, but all these kinds of profiles now get a suffix. And the suffix -f means that is specific for CANopen FD. And the -c means that one is specific for the old used generic classical CANopen. And we also introduced a -j for J1939 mapping of device profiles. So just a reminder for you, if you are looking to these device profiles, what is important for you when you want to implement the CANopen FD stuff are the ones with the suffix -f. Now, what changes with CANopen FD? You already heard that. So here, very briefly, we have an enhancement in the object dictionary. We have new service for client-server communication. We have an enhancement in the emergency service. We have now a conformance testing with the certificate, which is required. We have a new logo, obviously, which tells us this is a CANopen FD device, and we have a new physical layer. At this point, of course, I have to mention, nobody forces you to use bitrate switching, but as I already mentioned, the need for speed in the end of the day, when you have 64 bytes, then you would like to use bitrate switching and use a higher bitrate within the data phase. So physical layer. Now we are jumping into our next challenge, into challenge number 2, the physical layer. So first of all, when we're looking to our CAN bus structure and the impedance requirements, everything keeps pretty much the same. So if we are having a look to this schematic, to this drawing here, we're having 2 devices here connected via 2 wires, the CAN high and the CAN low signal, and having obviously termination resistors at both ends of the line. So this is like it used to be with classical CAN. And it's pretty much the same from the signal point of view. We have a differential signal here, so everything is fine. But if we take an oscilloscope picture, and it is still already the issue that this drawing here, that is the ideal drawing how a CAN system, a CAN network should be, but we all know it's not. We have a lot of cable stubs there. Maybe people are not using termination resistors at the ends of the cabling, but somewhere in the middle of nowhere, and things like that. So the assumption that the signal is like the red one here, that it's an ideally square wave signal of the CAN, is not true at all. It is something like the yellow one. So you typically have within your network, you have a ringing there, and that depends on how many devices you have there within the network, what kinds of CAN transceivers you need, how long are your stop lines in the network, and also on the used cable. And that means you have to consider there that this reflection is there, and this reflection means, especially for higher bit rates, this ringing means you're getting wrong bits at positions where you don't expect them, because the transceiver says, okay, this is a dominant bit or this is a recessive bit at this point where they are not. So this is a thing you have to consider when you're switching over to higher bit rates here. What does that mean for your CAN interface? When we have a look as typically a classical design of an isolated CAN interface, then we have there a DC-DC converter in there in our classical interface. We have there somehow a device which does the galvanic isolation, and we have our CAN transceiver there. There's a standard transceiver for classical CAN. So still the rules that we have to observe are pretty much the same for CAN FD that we have for classical CAN. That means use a common mode line filter. From my point of view, a common mode line filter saves your life. If you don't have that, you're in trouble. You will see that especially when you're doing EMI testing. The second important point, and especially important now for CAN FD and CANopen FD, is you have to observe parasitic capacitance. That means never ever even think of it that you put some kind of RC filtering in the end here of your CAN transceiver. That is no good idea at all. Next point is, of course, you should use a pull-up for digital CAN TX pin in your design. Most of the new CAN transceivers have a built-in pull-up resistor there, but not all of them. So keep that also in mind when you're using that. And never ever try to use a slope control. This is really counterproductive for CAN FD designs if you're moving to a higher bit rate. And now the most important fact is, when you set up design here, when you set up a kind of device with your galvanic isolation and you selected a kind of CAN transceiver for your application, in the end of the day, you have to measure the delay time for the transmitter delay compensation value setting, because what all these circuitry you have in there has a delay. So, and you have to keep in mind that for your setting within your CAN-FD controller, you need to measure the delay that starts from here, from the CAN TX pen, when the signal goes around here, the loop, and comes back to the RX pen. This is several nanoseconds. Of course, you can have a look in the data sheets and roughly calculate it from the data sheets. Our advice is take your oscilloscope, measure it, write the value down, and you need it later on then in your software. The next step you have to consider is that you might use so-called signal improvement capability transceivers, because with the standard transceivers that are available on the market, they are much limited with higher bit rates. And this is especially caused to the fact that the impedance of the transmitter changes between 30 ohms and 12 kilo ohms. And that depends if the transceiver is dominant or recessive. Because standard transceivers, if they are recessive, they're having a high impedance value. And this change between a high impedance and low impedance value, so in the meantime here, that causes ringing and reflection on the bus. So if you're using, like say, standard old-fashioned kind of transceivers, you will face the problem that if you're going up in the data phase to higher bit rates, that you will see much more ringing and reflections on the bus that you are used to see them, like when you use them on 250 or 500 kilobit with classical CAN. So that's the reason why I also mentioned with challenge number 1, have a closer look to the specification, especially to the CIA 601 series, which tells you something about the background about the signal improvement capability transceivers. Also, an important point is for these kinds of transceivers is that the slew rate of the transceivers from switching from recessive to dominant level and switching back from dominant to recessive level, they are they're typically with standard transceivers, there are much higher asymmetries in these timings. So you have, especially when you're switching on to FD, you have to look in the data sheet about these asymmetries between the rising and the falling edge. And especially, of course, also for these signal improvement capability transceivers, these timing asymmetries are tried to reduce much more than with your normal classical transceivers that are available. And these timing asymmetries, if they are there, they affect the worst case sample point that you can achieve. And this limits your highest possible bit rate within your CANopen FD network. So from our point of view, switching to these kind of signal improvement capability transceivers makes sense. So the good news is they are drop-in replacements. Means if you're already using a hardware design with a kind of transceiver in an SO8 housing, you can simply replace that. I selected here a part here in the drawing from NXP. It's the TGA 1462, but there are other manufacturers also offering these kind of transceivers. These devices have much better capabilities for higher bit rate than the existing devices which are available on the market right now. So from our point of view, if you're using, let's say, transceiver devices not compliant to the CIA 61-4, you will be typically limited to 2 megabit within the field. And it's quite difficult to achieve 4 megabit or more with these transceivers available right now. So now let's jump to the next challenge. We hopefully solved the physical layer, which is quite important. Now we have to select a CAN FD controller for our purpose. And how do we start with this kind of selection of the CAN FD controller? First of all, we have to look in the specifications and into CAN FD bit timings. If you have a look in the existing 1301, you will see that there are bit timings there for 80 megahertz clock. And you will now say, hey, why are you telling us something about a 40 megahertz clock here? The answer is, yeah, we have to rewrite the specification. The problem is, when we started with the development of the CANopen FD specification, we had in mind, okay, things are getting faster, and 80 megahertz clock on a Cortex M3 or M4 controller is no problem at all. But we learned within the CIA groups that there are devices in the market like Cortex M0 with a typical maximum clock rate of 48 megahertz. And so it's not possible to use a clock rate for the CAN FD of 80 megahertz. And so we said, okay, we have to move that way, that we use pretty much the same clocking on all devices. This is also quite important within the network. We need to use all the same clocking within these devices and have to use clock rates of 40 megahertz clock. And you see here the tables that we need for the nominal bitrate setting and for data bitrate setting for several bit rates. So for the nominal bit rates from 125 kilobit to 1 megabit, and for data bitrate settings from 1 megabit to 4 megabit here, and with their settings. An important point here in these tables, and that's the reason why I show these tables here, is the values that you see in the tables here for propagation segment, phase segment 1, phase segment 2, because that, in the end of the day, tells you where the sample point is, quite important. And this table tells you with this clock rate of 40 megahertz, you need exactly these values to achieve the settings that are desired. And now we are coming back to the question, what kind of CAN controller do I use? Before that, we do that. I have here another slide which tells us our possible bitrate settings that we have specified within the 1301. We have 6 data bitrate values from 1 megabit to 10 megabits. We have 4 mandatory pairs of bit rates, but our experience is that what I already mentioned is that bit rates greater than 4 megabits are really difficult to achieve with standard CAN transceivers on the market. And that is something you have to use these signal improvement capability transceivers. Now let's come back to the CAN FD controller and topics to consider when we select one here. You see here a picture of an IMX RT1170 family from NXP, quite a new device, having an ARM Cortex M7 inside. There are also derivatives available which have a second processor, a Cortex M4, for doing some additional support and lots of connectivity. This device tells us it has 3 times CAN FD. So if you select a controller like this one here, then the first thing you have to have a look into the data sheet is, does it support ISO CAN FD? You see here, I marked it in highlighted letters. ISO CAN FD is the important word. Why I am saying this? Because there are still silicon manufacturers on the market telling you, yes, we are using CAN FD, but this is CAN FD. They sometimes announce it as CAN FD version 1.0. And this was the first approach of Bosch, and it is not compatible with ISO CAN FD. So the first thing you have to have a look on is, does that thing really support ISO CAN FD? The IMX RT1170 does support that, but not as default. you have to find the little tiny bit inside some of these registers where you have to enable ISO CANFD in order to have fun with that. The next thing that you should have a look on is, are there any limitations on number of mailboxes of FIFO support? The reason why I'm saying that, because again, this kind of controller is, let's say, a kind of negative example, which doesn't give you the fun you were expecting. Because on the first pages of the datasheet, this device tells you, we support, of course, FIFO in our CAN. We support up to 64 mailboxes. We have filtering. There's everything available. Unless you enable ISO CANFD, then the number of mailboxes is reduced from 64 to 7. And FIFO support is not available any longer. So another point that you should have a look on is that, are these features that you need later on for your applications? And if you need them, you might get into trouble. Next limitation is, of course, the clocking. I already talked about 40 and 80 megahertz of clocking. So this should be possible with the clock tree to achieve these two possible clockings, especially now the 40 megahertz. The next point are limitations on CAN bitrate settings. The reason why I showed these tables concerning the nominal bitrate settings and data bitrate settings with all these values, they have a background, because in the end of the day, you need something about more than 300 time quanters in order to set up all these possible settings there. And if we have, again, a look in this kind of CAN controller family, you will notice then that the register size is limited. They limit it to somehow, if I remember it correctly, to about 100 or 120 time quanters. That means it is impossible to achieve those CAN FD bit rates, especially bit rates are lower than 500 kilobits and things like that. So another big limitation is the FD bitrate setting registers. So have a closer look on those one. We observed that already many times, that the setting possibilities are quite limited. And the last point where we think there is no fun at all is avoid external CAN FD via SPI. There are devices available on the market, but from our point of view, this is a real bottleneck. So typically, our approach for CAN controller access is to use a kind of generic model of CAN hardware. We have our API for that in order to support access to mailboxes, so-called buffers, message buffers, using transmit FIFOs, using receive FIFOs. And we observed that if you would like to have all these kind of features which are available, it makes sense that you select CAN controllers which use the Bosch MCAN core, because this original say CAN FD implementation offers, from our point of view, the most flexibilities. Okay, now we come to the last challenge, the challenge number 4, the protocol stack. So typically, if you already have an existing CANopen stack, you noticed from what has been changed, there's not much to do. Rainer and Oscar already gave an overview. So for most of the service, nothing has to be changed. Only the new services are emergency, which gets a new structure, and the new USDO service has been introduced. Also, within CANopen FD, there has been an object dictionary update, but from the point of view of the software, that's not a big deal. You simply insert some new objects and provide the information for them. Already, Rainer has showed to you this emergency protocol, which offers a greater payload, which now allows you to display logical device and specification. And at this point, I would like to point out why are there here reserved fields, and why are some of these so-called classical emergency error code definitions are at this plane of the structure and not elsewhere. During development, we said we would like to have access on structures as easy as possible. And that means if we would like to access a 16-bit value, like here, the CIA specification, we would like to have that on an even address boundary. So that's the reason why you sometimes find in those kinds of protocols reserved bytes there. Sometimes they're for the reason there has been an idea in advance, and it has been in the end of the day within the group we decided, okay, we don't need that anymore. Yes, that could also happen, but with these kind of new protocols, these reserved fields have been introduced to have access to structures from the programming point of view as easy as possible. That is also true for the new CANopen FD USDO service. Also here, Rainer introduced the new concept that we have now introduced: unicast, multicast, and broadcast communication. So we have a high transfer efficiency, and we can even use read-write multiple objects in one protocol. That will be the future for this USDO service. And this gives us lots of new possibilities. Here again, you already have seen these kinds of protocols. Here again, let me point you out that, for example, the reason why subindex is now in these new protocols in front of the index is just because of accessing structures. So the whole idea of these new protocols was also not to have new features, but also for you, if you're doing the implementation on your own, have it as easy as possible to do implementation of these kind of protocols. I don't go into details here because you have already seen those kinds of new services that we have from Rainer Zitzmann. Of course, in the end of the day, if you're writing now a CANopen FD software and you're using maybe your existing code, from our point of view, it makes a lot of sense to support both in your device, Classical CANopen and CANopen FD. So here's a part of sample code for two typical initializations. So if we would like to initialize a device like a standard CANopen slave stack, we using pretty much the same functions, but using different kind of values here. We're just saying here, you're a simple CANopen slave and using just one bitrate, one nominal bitrate. And if we're doing much the same for an FD stack, we're saying, okay, we configure you as a CANopen slave together with FD capability and supply here a second value for the data bitrate. Why? Because from our point of view, now we are in a situation that if you provide devices to customers, they are right now in the situation they would like to play a little bit, let's say it in that way, with CANopen FD, but still use the devices in their existing CANopen, classical CANopen networks. So I'm at the end of my presentation. Thank you for your attendance. And